Hello everyone, welcome to this session on Kubernetes Fundamentals. In this video, we will explore some core concepts of software architecture, particularly monolithic versus microservice, and understand why Kubernetes has become such a powerful tool in modern application deployment and scaling. By the end of this video, you will clearly understand what monolithic versus microservices are, what containers are, and how Kubernetes helps manage containers effectively. So let's get started. Let's discuss monolithic applications now. In the early days, most applications were built as monoliths. A typical monolithic application means everything is packaged together, usually as a single process, single binary, or one big package. All components like business logic, user interface, and database handlings are tightly coupled inside one unit. Monoliths can be a good choice if you are building small and simple applications that do not require frequent updates. But monoliths comes with major drawbacks. If one component crashes, the entire applications can go down because everything is tightly coupled in the monolith application. And deployment becomes risky since even a small update means redeploying the whole systems, which can break things in production. And scaling is also difficult. If you want to scale one feature, you still need to scale the whole applications because all features are tightly coupled in monolithic applications. And as applications grow bigger and more complex, these limitations becomes a serious problem. That's where microservice architecture comes in. Let's discuss microservice architecture now. Microservices solves many of these challenges. Instead of building one big block, we split the application into multiple smaller independent services. Each service is responsible for a specific business function and we call this as a microservice. And what are the benefits of microservices? Each service can be developed, deployed and scaled independently. And faster deployments and updates since changes in one service don't affect the other service. And the last one is teams can work on different services without blocking each other. However, microservices bring complexity and that's where the containers and Kubernetes play a key role. Let's discuss containers now. Containers are lightweight, portable environments that include everything your application needs to run, including the code, libraries and dependencies. This makes them consistent across development, staging and production environments. And why containers are great for microservices? Because each service might use different programming languages and different frameworks and dependencies. So for example, one microservices could be written in Python, another one in Java, and other microservices could be written in Node.js. Managing all these differences on the same servers can get messy sometimes, okay? And that's where container comes in. A container packages the microservices along with everything it needs, making it portable, isolated, lightweight and scalable. So in short, microservices gives us flexibility in design, containers gives us consistency, portability and efficiency. Let's discuss container engine now. Alright, we have seen how containers makes microservices portable and efficient. But how do these containers actually run on our systems? That's where container engine comes in. Container engine is a software that creates, runs and manages containers on our machines. The most popular engine is Docker. Docker allows developers to build container images, run them as containers and manage them easily. Other container engines like Containerd and Creo are also exist. And what are the responsibilities of container engine? Creating containers, isolating them, managing resources, handling lifecycle events. In simple terms, the container engine is the backbone that powers containers. Let's discuss container basics now. First, container image. Think of a container image as blueprint. It is a read-only template that contains your application code, libraries, dependencies, and configurations. Example, a Python web application image with Flask pre-installed. Next, container. A container is a running instance of an image. If the image is the blueprint, then the container is the actual house built from that blueprint. You can run multiple containers from the same image. Next, container registry. Now, where do we store images? In a container registry, right? Docker Hub is a public repository. Private means Amazon ECR, Google Container Registry, Azure Container Registry. Registries acts like a library of containers, images that you can pull and run anywhere. Dockerfile. Dockerfile is a simple text file that defines how to build container images. It contains instructions like what base image to use, example Python or Ubuntu, what dependencies to install, what command to run when the container starts. Next, Docker Compose. Running a single container is easy, but most real-world applications need multiple containers working together, like web application container plus database container plus caching container. That is where Docker Compose comes in. It is a tool that lets you define and run multiple container applications using a single YAML file. For example, one service for your application, one service for your database, one service for your caching layer. With one command, Docker Compose can spin up all of them together and manage the connections. So to recap, Dockerfile is a text file, image is the blueprint, container is a running instance, registry is the library of images, Docker Compose is orchestration for multi-container applications. And these basics forms the foundation before we move into Kubernetes. So far we have learned what containers are, how images, registry and Docker works. Running a few containers is simple, but what if we have hundreds or thousands of containers across multiple servers? So there will be some questions like how do you restart containers if they crash? How do you balance traffic between the containers? And how do you scale them up or scale them down automatically? And how do you deploy updates without downtime? So managing this manually would be almost impossible. That is exactly where Kubernetes comes in. Handling this manually would be difficult and unreliable. That is why we need something smarter to manage it all. This is where an orchestrator becomes essential. Kubernetes is a container orchestration platform. That means it automates deployment, scaling and management of containers. How Kubernetes helps automated scheduling and deployment. It places containers on the right servers. Self-healing. It restarts or replaces containers automatically if they fail. Load balancing and service discovery. It distributes traffic across the containers. Scaling. Scaling up during high demand. Scale down when traffic drops. Rolling updates and rollbacks. Update applications without downtime. Rollback if needed. Resource optimization. Uses resources efficiently and saves cost. Kubernetes takes away the pain of managing containers manually. It gives you a powerful system to run applications at scale, reliably, efficiently, and automatically. That is why Kubernetes has become the industry standard for running modern applications. Alright, that's for today's sessions on Kubernetes Fundamentals. If you found this video helpful, don't forget to like, share and subscribe for more DevOps and Kubernetes content. In the next video, we will dive into Kubernetes architecture, breaking it down step by step from container images to how they run inside pods. Thanks for watching and I'll see you in the next one.